Hi students, today we're going to be doing some practice problems using the ideal gas law and the combined gas law. Real quick review, remember the factors that influence each other in terms of a gas are the pressure that the gas has, and we use a P to show that. The temperature of the gas definitely has an impact on the characteristics of the gas. The volume of the container that the gas is in matters, and the amount of gas that we have in moles, or the number of particles, and that's going to be noted with an N. So remember, the combined gas law is used whenever there's a change in the system. So maybe we have a certain amount of gas in a container and we heat that gas up and we want to know what the new pressure is. And that's when we use the combined gas law. So the combined gas law, remember, is P1 V1 over N1 T1, where the subscripts are just saying the initial conditions of the gas, or one set of conditions, is equal to P2 V2 over N2 T2. So the initial conditions of the gas will always be equal to the same as the final conditions of the gas. And remember, when you learned about the combined gas law, you learned about direct and inverse relationships between these different variables. Now, the ideal gas law is just a rearrangement of this equation, PV equals nRT. And in this equation, the R is the ideal gas constant. And so we're going to need to use that number anytime that we're working with the ideal gas equation. When do we use the ideal gas law to solve a problem? That's where we have just one set of conditions. There's no change in the system necessarily, and we are missing one of the variables. So for instance, maybe I have a balloon at a certain pressure. I know the volume of the balloon and I know the temperature of the balloon, but I want to know how many moles of gas are in that balloon so I can do some stoichiometry with that. This is when I would use the ideal gas law because there's no change in the system. I'm just solving for a missing variable. So, sum it up, the combined gas law is used when we have a change, and the ideal gas law is when we're just missing a variable. All right. Now let's go through some of these practice problems. Number one, and for each one, the first thing we're going to need to decide is which of these two equations are we going to use to solve this problem. Number one says if 4 moles of gas, I'm going to underline things we know here, are at a pressure of 5.4 atmospheres and have a volume of 120 liters, what is the temperature? So the question mark I'm looking for here is temperature. I'm given moles, atmospheres, and liters, and I'm looking for one missing variable. Notice there's no change in this. It doesn't say the pressure changed or the volume or temperature changed. And so this is an ideal gas law problem. We're going to use PV equals nRT. Let's write down our variables. So we're given N is 4 moles. And I'm going to write my units here because that's going to become important when we choose our R value that we're going to use. N is 4 moles. We have our pressure is 5.4 atmospheres. Again, units very important there. The volume of this gas is 120 liters. And I'm looking for temperature. The first thing I could do here is go ahead and rearrange my equation to solve for temperature. So I want to solve for T. I'm going to divide both sides by nR. So I get temperature equals PV divided by nR. Now I have my moles, my pressure, and my volume here, but I don't have the R value. So how do we decide what R value to use? And the answer is we want to look primarily at our pressure units. There are an infinite number of R values, just depending on what units you're using. Maybe not infinite, but there's a whole bunch of them. The main ones that we will focus on is the ones that have different pressure units. And so In the notes for the ideal gas law, you were given 3 different R values, the one for atmospheres, the one that's used with kilopascals, and the one that's used with millimeters of mercury. So we want to just look at our pressure units. And if we see here, we're in atmospheres, which means we need to use the R value that has the units of atmospheres in it. And if you're not sure what the R values are, go back into those notes that are linked on the main lesson sheet and check those R values. And you'll want to have those handy, so they're also in your course pack. You can look in there as well. So the R value that we want to use here, I'll write that down here, is the 0.0821. 0.0821, and the units on that are liters times atmospheres over moles times Kelvin. We're going to go ahead and put all those units in to make sure that they cancel out here. All right, let's go ahead and plug our numbers in. So pressure, 5.4 atmospheres. Okay, my volume is 120 liters. And I'm going to divide that by my moles, which is 4 moles, times my R value, which is 0.0821 liters atmospheres over mole Kelvin. Okay, now let's take a look at our units really quick. All the units in our R value should cancel out except for the temperature units, which is over here, and because that's what we want to be left with. So let's check that out. Here I have moles here and moles here on the bottom, so those will cancel. I have atmospheres on top here, and I have atmospheres here, and I have liters here and liters here. So all of my units cancel except for Kelvin, and that's what I want. That's a temperature unit. So we're going to go ahead and punch this into the calculator, making sure that we multiply these two numbers together before we divide on the bottom. And let's see what we get. When we punch that into the calculator, we get 1,973 degrees Kelvin. Okay, that's pretty hot. Now, one thing we want to be paying attention to is significant digits here, which is a little bit of a problem because we have 4 moles as a word instead of an actual number. So if we write that, I guess we could assume it's 4. Maybe it's a counted number and we have an infinite number of zeros on the end there. At the least, we should have only 2 sig figs because 5.4 and 120 are both 2 sig figs. So if I wanted to round this to sig figs, I would round up to 2,000. But I can't make, this only has 1 sig fig, so I could write this as 2.0 times 10 to the third, 123 Kelvin. Okay, to pay attention to the sig figs. All right, so that's an example of using the ideal gas law. So let's go to the next one. This one says initially I have a gas with a pressure of 84 kilopascals and a temperature of 35 degrees Celsius. I heat it an additional 230 degrees. What will the new pressure be? Assume the volume of the container is constant. So automatically we see that there's a change in the system here, and it asks us what will the new pressure be. That's a dead giveaway that we need to use the combined gas law here because there's been a change and we want to see what the new, in this case, the new pressure is. So let's go ahead and write out our variables here. Initially, so that's going to be P1, okay, my initial pressure is 84 kilopascals. And it has a temperature, initial temperature of 35 degrees Celsius. That's going to be important. We're going to need to convert that. And I heat it an additional 230 degrees. So I'm not given a volume here, but that doesn't matter because if the volume stays the same in the equation, then we don't need to include it. We'll go ahead and write everything in here. It also doesn't say anything about the number of moles or gas being added or taken away, so the only thing that changed here is the temperature. So let's write out the whole gas law. P1 V1 over N1 T1 equals P2 T2 over N2 T2. Oops, sorry, this is supposed to be, see if I can erase that. Yeah, that's supposed to be a V2 right there. All right, now which variables do we not care about here? We know pressure changes and temperature changes, and so we need to keep these two in the equation, but the volume is constant, so it's going to cancel out, and it doesn't say anything about changing the amount of gas, so moles will be the same. So if I rewrite this equation now, I get P1 over T1 equals P2 over T2. Okay, now what is P2 and T2? We're given that T2, and I'm going to draw a line here between the before and after. So this is initial and this is final. T2, it says that we've heated this an additional 230 degrees, and so basically we need to add 273, so 35 plus 273. Okay, when I add that up, it gives me 298. Oops, that's not correct. Sorry. I'm thinking of the conversion here. It heats up an additional 230 degrees, so 230, and that's going to give us 265 degrees Celsius. All right. Now there's a issue with our pressure units here. Our temperature units. Our temperature cannot be in Celsius. It needs to be in Kelvin. To convert, we are going to add 273 to any temperature that's in Celsius. So we're going to do plus 273 plus 273. And when I add those up here, I get 298 Kelvin, and for this one I get 528 Kelvin. You have to remember to convert Celsius to Kelvin if that's a factor in the problem. Kelvin's an absolute scale. It starts at 0 and just goes up. Celsius has positive and negative degree temperatures, and so that can really mess up our calculations here. So it's important that we use these numbers in Kelvin. And guys, remember, we're looking for P2 here. That's what we're looking for. Let's go ahead and solve this for P2, and then we'll go ahead and plug numbers in. So I want to isolate P2 so it's by itself, which means I need to move T2 to the other side. P2 is being divided by T2, so I'm going to multiply both sides by T2. Okay, those will cancel, and I'll get the new pressure, P2, is equal to P1 times T2 over T1. And now we can go ahead and plug that stuff in. So P1 is 84 kPa, kilopascals, times temperature 2, and Kelvin, remember, is 528 Kelvin. Okay, divided by temperature 1, which is 298 Kelvin. When we plug this in, well, actually, let's look at our units really quick. Over here, we have Kelvin on top and Kelvin on bottom, so that's going to cancel. We're looking for a pressure, and we're left with pressure units here in kilopascals, so that's going to be my units when I solve for P2. When I plug this into the calculator, I'm going to get 150 kPa. Now, this is a good one where we can do a quick gut check. Our temperature went up. What's the relationship between pressure and temperature? If the temperature goes up and the volume of the container is constant, it doesn't expand or contract or anything, then the pressure must also go up. And that's in fact what happened here. We went from 84 kilopascals to 150 kilopascals. So our quick gut check on this, it makes sense. If the temperature went up, the pressure should also go up. Okay, so good practice using the combined gas law here. All right, next one, my car has an internal volume of 2,600 liters. If the sun heats my car from a temperature of 20 degrees Celsius to a temperature of 55 degrees Celsius, what will the pressure inside my car be? Assume the pressure was initially 760 millimeters of mercury. Okay, now is there a change in the system? Yeah, right. The sun changed the temperature of the car from 20 to 55 degrees Celsius. And so we want to know, what's the new pressure going to be here? So let's see which gas law are we going to use. We're going to use the combined gas law here because we have a change in the system. My car has an internal volume. So now think about this volume. Is the volume inside of the car going to change? It's not. It's a solid, rigid structure. So it's going to start out at 2,600 liters and it's going to stay that way, which means we don't need to include volume in this equation because it stays constant and we're using the combined gas law here. But the temperature changes, so we know we're going to need to have T1 equals 20 degrees Celsius, which we're going to have to convert that. T2 is 55 degrees Celsius. Again, I'm going to split these up so I've got a before and after, an initial and a final. And it says, what will the pressure inside my car be? Assume the pressure was initially 760 millimeters of mercury. So P1 equals 760 millimeters of mercury, which is a pressure unit. Now, it's asking for the final pressure, P2. Now, what about the other variable here? This is a combined gas law problem. What about the other variable, the moles? Is the amount of particles of gas going to change inside that car? The intention here is that it's not going to. We're just going to assume that it's a sealed up car, even though most cars probably leak a little bit of air inside and out. But let's just assume that the amount of particles we started with in moles stays the same inside of that car since it's a sealed or closed system. Okay, so we're solving for P2. Let's write out our gas law. And this time I'm going to skip writing down the variables that we don't need. So it would be P1 times V1, but I don't need the V1 because volume doesn't change, equals N1, which I don't need because the moles doesn't change, times T1. Okay, equals P2 over T2. So those are the variables that I need to work with here. Okay, don't forget we need to change Celsius to Kelvin. So add 273, and that's going to give us 293 Kelvin here. And when I add 273, oops. Okay, let's try to fix that here. And I add 273. Goodness. When I add that, it's going to give me 328 Kelvin. All right, now we're looking for P2, so let's rearrange this, and we're going to multiply both sides by T2. So P2 equals P1 T2 over T1, and we can go ahead and plug these numbers in. Pressure P1 is 760 millimeters of mercury, and T2 is 328 Kelvin, and we're going to divide that by T1, which is 293 Kelvin. And look at our units. Again, I have Kelvin and Kelvin, so those cancel, and I'm left with millimeters of mercury, which is a unit for pressure, and I'm looking for a pressure. So that's good. It means I most likely set things up correctly. Okay, whenever we solve this, multiply our numbers on the top, divide, we're going to get 850 millimeters of mercury. Okay, so another good practice using the combined gas law. Sig figs here, I only have one sig fig up here, so technically I should round this to 900 millimeters of mercury to be paying attention to sig figs. Okay, let's do a couple more. Now number 4 is asking, in the car above, in the problem above, how many moles of gas are in the car? So what are we going to use here? Number 4, we're just looking for one variable that we don't have. And so we're going to use the ideal gas law for this one. But then you might say, well, what conditions should I use? Do I use the P1, T1, this set of conditions, initial, or do I use these here? And the answer is it doesn't matter. Just pick a set. And we have our volume here. Let's go ahead and use the initial conditions since those were given to us. We have already converted. We have our temperature, we have our pressure, and now we can go in and find moles using the ideal gas law. So let me convert these numbers down here. Volume equals 2,600 liters. Pressure temperature, short-term memory loss here. Okay, 760 and 293K. And 760 millimeters of mercury. Again, these units here, this is going to be important because it's how we're going to pick our R value. We are looking for N, the number of moles, and we also need to go find our R value. Now our R value is going to be the one that has liters, Kelvin, and millimeters of mercury. So if you go back to your notes or look in your course pack, or you can even look it up online, but you're going to see a lot of other R values there, so you have to be careful if you do that. The correct R value for this one that's in millimeters of mercury is 62.4. 62.4, and that's going to be liters times millimeters of mercury over moles times Kelvin. All right, ideal gas law, PV equals nRT. PIV-NERT. Just be careful how you say this. Okay, we're looking for N, so let's rearrange our equation. We're going to divide both sides by RT, divide by RT, and we get that the amount of moles is equal to PV over RT. Okay, real quick unit check. Pressure, I've got units there, liters, Kelvin, looks like we're all good. We can plug these in. Pressure is 760 millimeters of mercury times the volume, which is 2,600 liters. If you do other problems like this, or you look other ones up, you might get pressure or volumes in milliliters. You might get all different kinds of pressure units. There's a lot of variability in there. So just know that a lot of times we simplify things for you a little bit to not get too overwhelming. But the real world has a lot more units to work with than we always show you in class here. And then the temperature is 293. Okay, and let's go ahead and look at our units here. Again, I've got millimeters of mercury here and here, they cancel. I've got Kelvin here and here, they cancel. And I've got liters here and here, they cancel. I'm left with moles, and I'm looking for moles, and so that's good. And we're going to go ahead and plug this into, plug this into the equation. And when you solve for this, that should be an N. I can erase that. N is 108 moles of gas. Okay. If you used the pressure and temperature for the initial or the final set of conditions, up here you'll get the same number, or really close, depending on rounding that you did. So it should be the same amount. Okay. All right, let's do another one here. Number 5, a toy balloon filled with air has an internal pressure of 1.25 atmospheres and a volume of 2.5 liters. If I take the balloon to the bottom of the ocean where the pressure is 95 atmospheres, what will the new volume of the balloon be? And then this is a two-part one. It says, and then how many moles of gas does the balloon hold? And it's saying assume the temperature is 285 Kelvin throughout the whole process here. So to answer the first part, what will be the new volume of the balloon? Again, new volume means there was a change in the system. We're going to use the combined gas law here. All right, so what do we have here? The internal pressure, so P1 equals 1.25 atmospheres. And as a volume of V1 equals 2.50 liters. Okay. I take the balloon to the bottom of the ocean. The pressure is 95 atmospheres. So I have a new pressure, P2 equals 95 atm. And it's asking what's the new volume going to be. So the final volume, what's that going to be? Now, what about moles and temperature? The balloon, it's a toy balloon. It's a sealed system. We didn't add gas or take away gas. We just took it to the bottom of the ocean. So we're not changing the amount of gas in there. We're just changing how those particles are spaced. And then also here, the temperature, we're going to assume that that remains constant because it doesn't talk about any kind of a temperature change. So when I write out my combined gas law, I don't need to include the volume, I don't need to include moles, and I don't need to include temperature. So P1 V1 over N1T1, well, we're going to leave out temperature and we're going to leave out moles, and so we don't need those, equals P2 V2. If it helps you to write all the 4 variables on each side and then cross out the ones you don't need, you can do it that way. And if it helps you to go ahead and write the numbers for all of them, you can do that if you have them. It just saves time to do it this way. Okay, we're looking for V2, so let's solve for V2. I need to divide both sides by P2 to rearrange P2. Those will cancel. V2 is P1 V1 over P2. Let's go ahead and plug these in. P1, 1.25 atmospheres. Okay, and then V1 is 2.50 liters divided by P2, which is 95 atmospheres. Units, atmospheres cancel. We're going to be left with liters. That's what we're looking for here. And so whenever we plug that in, we are going to get 0.033 liters. Okay, so the new volume equals 0.033 liters. Now, if we do a quick gut check on this, does that make sense? If we put a higher pressure around the outside of the balloon, around that gas, and that means the pressure of the gas is going to have to equal the outside pressure around it. So if we increase that pressure around the balloon, it's going to decrease the volume of the balloon. That's what this is saying. So that makes sense. Our volume went from 2.5 liters all the way down to less than 0.1 liters. So it greatly reduced the volume of that flexible balloon. Part 2 of this problem is asking how many moles of gas are in the balloon, and so we again can use either the initial or the final information, but because we're just looking for moles here, we want to go ahead and use the ideal gas law. So we're going to go ahead and use, let me erase this stuff here. We'll use PV equals nRT. We'll get it pretty well. Okay, so PV equals nRT. And let's just forget about this stuff here, and we'll use this initial set of conditions. Now, this here, let's rearrange that to solve for moles. And so I'm going to divide by RT, divide by RT. So moles is equal to PV over RT. Now we have our pressure, we have our volume. What's our temperature? 285 Kelvin is given to us here, so T1 is 285 K. And then we need our R value. So again, we're going to look at our pressure units. Our pressure units are in atmospheres, so the R value that we're going to use in this equation is the 0.0821. 0.0821. So when we go plug this in, we have 1.25 atmospheres times 2.50 liters divided by R, which is 0.0821 times temperature, 285. All right, and when we plug all that in, we should have 0.13 moles of gas. Okay. So again, that was a 2-part problem. We used both the combined gas law and the ideal gas law, just depending on what we were looking for. Let's do one more problem here. An oxygen cylinder contains 522 grams of oxygen gas at a temperature of 45 degrees Celsius. The cylinder has a volume of 3.5 liters. What is the pressure in the cylinder? Now, what should we use here, combined or ideal? This problem does not have a change. We're simply looking for the pressure of this cylinder, and we're given temperature and volume. Now we have one issue. We're given grams of a substance, and that's not a part of this equation. PV equals nRT. Grams is not in there. However, because you are experts in chemistry, you know how to convert grams of oxygen gas to moles of oxygen gas. So that's something that we're going to have to do, and we will frequently have to do that whenever we're working with moles of gases or grams of gases. We have to convert between those two. So let's write down what we have here. We know we have 522 grams, and we'll go ahead and get the moles for that. So we'll do that in just a second here. We have a temperature of 45 degrees Celsius, and we're going to convert that to Kelvin in a second. The volume, we don't have to do anything with that, 3.5 liters, and we're looking for pressure. Okay, so let's go ahead and convert grams of oxygen gas to moles. How do we go from grams to moles? We need to go from grams of O2 to moles of O2. So what's the molar mass of oxygen? 16 plus 16 is 32 grams per mole. We'll calculate that in a second. We're going to also need to convert our 45 degrees Celsius to Kelvin by adding 273 degrees. We get that calculation. We also need to find our R value. In this, we have for our pressure units, actually we don't have pressure units because we're looking for pressure. So what that tells you is you can pick any R value that we've given you, and whichever one you choose, the units will be your pressure units that are attached to that R value. Let's go ahead and use the one that we haven't used yet, and that's the 8.31, and that's in kilopascals. Okay, so we'll just use one that we haven't used yet. Let's go ahead and do a couple of calculations here. So I went ahead and calculated our moles of oxygen gas and our temperature in Kelvin. We have our volume in liters, and we have our R value we're going to use down here. And we're looking for pressure in this case, so we're going to divide both sides by volume. Divide by volume, that'll cancel. And we have pressure equals nRT over V. N is our amount of moles, so we have 16.3 moles. R is 8.31, and the units here are going to be liters times kilopascals over mole times Kelvin. And then we have temperature on top here, which is 318 Kelvin. And we're going to divide all of that by the volume that we have, which is 3.5 liters. Let's check our units here. I have moles here and I have moles here, so those cancel. I have liters here and liters here, those cancel. I have Kelvin here and Kelvin here. I'm left with my pressure units of kilopascals, so whenever I get my answer, my units are going to be in kilopascals. Let's go ahead and calculate that. So our pressure would be 12,306 kilopascals. I'm not paying real good attention to sig figs here. I want to keep that in mind as we're doing these because we've got measured numbers, but really my intention here is to focus mainly on using these different gas law problems. Okay, let me see if there's one more we can look at here. All right, we're going to go ahead and stop there. If you would like to work through any of those other problems and check the key, I will make that available to you. But these are the kinds of problems that you're going to need to be able to do with the combined gas law and the ideal gas law. Thanks for listening.